Okay, we're going to think about waves to begin with. So we've got two types we need to consider. We have longitudinal and transverse waves. And they're distinguished by the relationship between the oscillations of particles in the wave and the direction in which the wave is travelling. So if we've got a longitudinal wave, particles oscillate parallel to the direction the wave is travelling. An example of this would be a sound wave, in which we might have a bunch of particles here, and as they're made to vibrate, they oscillate backwards and forwards, banging against one another, and they create regions where they're bunched up, called compressions, and regions when they're further apart, called rarefactions, and the sound energy is transmitted in that direction. So you can see that these particles are moving forwards and backwards, and the sound wave is travelling in that direction. So this would be called a longitudinal wave. And more commonly, we have transverse waves, in which the particles oscillate at right angles to the direction the wave is travelling. So, example of this would be a water wave. Here we've got particles. If we pick a point here, it's going to be oscillating up and down, or point here is going to be oscillating up and down as the wave travels forward in that direction. So you can see the particles are oscillating up and down, the wave is travelling forward, the particles are oscillating at right angles to the direction of the wave. Common forms of transverse waves would include any wave in the electromagnetic spectrum. So that's light waves, infrared, ultraviolet, microwaves, X-rays, gamma rays, and so on. Okay, so that's a couple of basic words. Let's think as well about other terms that we need in order to describe waves. Any wave is a repeated motion, and we use some words to describe the amount of time it takes for a wave and the amount of distance a wave takes up. So the time period of a wave is just the time it takes for one full wave. The time taken for one full wave. If I was drawing a wave, we would indicate it, for example, like that, an oscillation which goes up, then down, and returns to its starting point there. That would be a full wave. And the time period is the time it takes, which would normally be measured in seconds. The other word we use to describe the proportions of a normal wave is wavelength, and as the name suggests, that's just the length of one full wave. The distance from one crest to the next. So if I was drawing my waves again, I label a couple of the crests, and we have a length there, a distance there. We often give this the symbol lambda. Lambda is the symbol for wavelength, and it's usually measured in meters. Linked to time period, we have frequency. The frequency, as the name suggests, is to do with how many waves we get per second. So the frequency of a wave is the number of waves or oscillations passing a given point in 1 second. Okay, so it's a number of waves per second, and we sometimes measure it in per seconds or seconds to the power minus 1, which is a bit of an odd sounding unit. More commonly, we measure it in the unit of hertz, which is symbolised or abbreviated with just Hz. So 1 wave per second is 1 hertz. You also need to remember things like a kilohertz. A kilo is 1,000, so 1 kHz, 1 kilohertz would be 1,000 hertz, 1,000 waves per second, and a megahertz would be 1,000,000 waves per second. So we've got frequency. Now, if you think about it for a minute, frequency, the number of waves per second, is going to be related to time period. The longer the time it takes for a wave, the fewer you're going to get per second, and the other way around. The more waves per second, the shorter the time period. So in fact, these are related using this equation, t equals 1 over f, and f equals 1 over t. What does that mean? It means that the time period is 1 divided by the frequency is 1 divided by the time period. So let me give you an example. Suppose the frequency is 0.1 hertz. Pause the video, see if you can work out what the time period is. Okay, we've got a frequency of 0.1. Let's substitute into the equation. The time period is 1 over 0.1, which is going to be 10 seconds. And we can go the other way as well. Suppose the time period is 0.2 seconds. What will the frequency be? Pause the video and see if you can work it out. So fairly obviously here we've got to use this second formula. Frequency is 1 divided by time period, 1 over 0.2, which might not need a calculator to tell you, is going to be 5 hertz, 5 waves per second. So that's the link between frequency and time period. One more term that we use when defining waves is amplitude, and the amplitude is a measure of how large the disturbance is in the wave. So if I picked a wave like that, we call that small amplitude. If I picked a wave like this, we'd say that's got larger amplitude. And we define the amplitude by taking the middle, or the equilibrium position, and looking at the distance between the middle and the maximum displacement. So the amplitude is the distance from the midpoint to the top of a crest to the point of maximum displacement from equilibrium. Notice, by the way, you can define amplitude perfectly well just using a diagram like that. You don't really need words. A diagram like that defines amplitude perfectly well. And as you may know, if this was a sound wave, then a low amplitude would be a quiet sound, a large amplitude would be a louder sound. So amplitude is the physical property that underpins our sense of volume. Similarly, if we looked at low frequency waves, not many waves per second, and compared them to high frequency waves, lots of waves per second, low frequency would correspond to low pitch, high frequency would correspond to a higher pitched